today's International Inverse Problem Seminar. So we are very happy to have Jianliang Qian with us today, which will be talking about a fast butterfly compressed Hadamard-Babich integrator for high frequency equations in inhomogeneous media with arbitrary sources. Thanks a lot for giving a talk today.
Oh, thanks, Kanu. Thanks, Katia, for the invitation. I'm really pleased to give this presentation on my work related to high frequency waves. This is joint work with Yang Liu. He's at Berkeley Lab, and Jin Song, he was my student, now that's working at Synopsys semiconductor software company. Bob Bridge, many of you know him. He's really a gentleman and still active on the various things related to geometric optics, and I learned from him a lot during the past more than 20 years. So here's the question that we would like to develop microlocal analysis-based algorithms for computing high-frequency waves in homogeneous media with some desired properties. Why we are interested in these, essentially is thing why we are interested in these tools, what kind of benefit we can have. Because wave propagation everywhere, so we would have methods which essentially follow the Shannon's sampling principle. Essentially says that we will specify a fixed number of points, like 4 to 6 mesh point per wavelength, to compute a wave. Because the wave depends on wavelengths, and then if we do not provide sufficient sampling of the signals, then we will have aliasing, and these will not be good. However, we also don't want to oversampling. To be oversample, that means we will waste lots of computation cost. So that's the motivation. We would follow so-called Shannon sampling principle. No oversampling, no downsampling, those kind of issue. Uniform accuracy with respect to frequency. That means no matter how high the frequency is, we will keep only 4 to 6 mesh point per wavelength. Okay, there's a kind of accuracy, uniform accuracy with respect to frequency. That means when frequency becomes higher, and our accuracy will become better in terms of our methodology here. Scalability and the overall CPU time and memory requirement, we would have a linear complexity algorithm or n log n type of complexity that's almost optimal. Okay, that's our motivation. Also, we would like to handle multiple frequencies and multiple right-hand side simultaneous. That means we will set up some mechanisms so that once we have the mechanism in place, then we can use those mechanisms to compute the multiple frequencies without changing anything else. And multiple right-hand side, will be very extremely useful for imaging inverse problems. Okay, so this is also the feature we would have. Applicable to acoustic waves, elastic waves, electromagnetic waves, and those all those we can ask inverse problem imaging. So this, if we can have such a method, then these are of course very significant. So can we have such solvers? Let's start with the Helmholtz equation. We would find the solution to the Helmholtz equation with a variable refractive index substitute to arbitrary source. Okay, that's the right-hand side. Here's the arbitrary, essentially, not just a point source, and that's allows to handle the kind of inverse scattering problem easily because we will have some kind of right-hand side perturbed. So here n index refraction or Sloan's function is a variable, okay, in homogeneous media, okay. Then omega large angular frequency, so certainly we will impose the so-called small field radiation boundary condition at infinity, okay. So if on the source function right-hand side point source, then we will have a so-called green function, okay. So that's the okay. So now we talk about discretization. We try to solve this Hadamard equation. We are given volumetric discretization of a computation domain with n degree of freedoms. Okay, so that's Jianliang principle observed. That means omega h equal to O1. That's essentially we these are allowed to have a fixed number of points per wavelength in terms of sampling. Okay, that's neat. Then this essentially mean that total number of degree of freedom will be proportional to omega to the this power. Okay, so that's the total number of degree of freedom we would have when we try to solve wave Hadamard equation or wave equation and so on. So we can use a variety of discretization methods like finite difference, finite element, those standard numerical methods, or we can use a hybrid asymptotic finite elements method. All those methods will give us n by n linear system. Okay, we design numerical scheme to have two properties. Okay, we would have almost linear complexity up to polylogarithmic factors in both CPU time, memory storage units for solving linear system. Okay, that's the linear complex, and having asymptotic uniform accuracy with respect to 1 omega at least. Okay, as omega going to infinity. Okay, and at the same time that Jianliang sampling principle should hold. Okay. Okay. Why we design those two properties? Okay, because when we design those things, that means we don't have. Okay, so why we have? So if we just solve the linear system and by linear system by direct or iterative methods, those methods will be very expensive in memory and CPU time. So in the worst case scenario, in terms of CPU time, then we will have O(n) cube. So imagine that three-dimensional situation. Each direction we sample by 100 points. Then total n will be 1 million. 1 million that 10 to the 6. And now taking a cubic, that's 10 to the 18th. So that's a huge number of computation cost. Okay, so that we try to avoid. Another issue related to direct methods, that's so-called pollution error. Okay, dispersion error. Okay, so Babich, Sorter, and Graham Sorter, they have analyzed essentially mean that for high frequency problem, oversampling is required for reasonable accuracy. That means sampling principle will be violated if we would have reasonable accuracy by using direct method like finite element or finite difference methods. Okay, so this means we will have suboptimal degree of freedom. That means we will not able to have this kind of we will have a large number of degree freedom. Okay, and now in the high frequency regime, we in our setup here, our convergence will be measured in a different way. Okay, because the pollution error, so standard method for Helmholtz equation error will does not decay as h going to 0 if omega h is fixed. Okay, just reasoning from pollution error. So that means we would, if in the high frequency regime, we will ask differently. So we will seek, when omega going to infinity, we seek a numerical method which both converge asymptotically with respect to omega and obey Shandong principle. Okay, so at the same time, we will make omega h to be fixed. Okay, to be fixed. Okay. So far no methods until our methods. Okay, so that can achieve those two properties. So that's essentially here they talk about. Okay, so what we will do here, we will essentially use the green function. If we know the green function of Helmholtz equation, then the solution can be written down like this. Okay, just an integration. Okay, integration of green function with respect to the source function. Okay, so this is the essential solution formula. Now the assumption here that the green function is given, then we just need to carefully develop a good method, fast algorithm to evaluate this integral. Okay, so so essentially we have two things to deal with. First, how do we obtain such kind of green function? Okay, that we will use Hadamard-Babich ansatz, okay, to obtain this green function, construct this green function, and how to evaluate this integral rapidly. So that we design so-called hierarchical off-diagonal butterfly algorithm to compress this integrator. And then once we have this integrator, compressed, that we can apply this integrator to the source function up to our choice. We can, once we have this integrator, we can apply this integrator to many different source functions, okay, as we wish. Okay, so that gave us our linear complexity in both CPU time and memory storage cost and uniform accuracy with respect to omega. Okay, so that's the essay. Okay, so how do we compute this green function first? Okay, so this is the Helmholtz equation now with just a point source. If we use a traditional geometrical optic ansatz, then we are able to have scale separation. And scale separation means that we just need to compute two sets of function. One is tau here, that's a phase function. There's you see we have oscillator omega from different from this tau here. That's a exponential function here, depending on omega and tau will capture the oscillation. Then this amplitude related thing will try to modulate those oscillation. Okay, and using the ansatz, we end up with two equations. One is a Coulomb equation for the travel time or phase function with associated with a point source condition. Then amplitudes. Okay, amplitudes for transport equation. And so the issue is that how do we solve these linear system? These two set of equations. You see that once we are able to solve these computed tau and amplitude, and then because scale separation here, essentially we have a family of solution for all omega. Okay, if we solve this obtain those two set of functions, then we have a family of solution for all omega. So that means that's a good thing about these geometrical optic ansatz. So we have scale separation. Once we have the ingredients, we have a family of solution. The issue is that we don't know how to initialize these amplitudes as a source point. Okay, so because when in 3D, these amplitudes will proportional to 1 over the distance. Okay, 1 over distance. Okay, then these when the source observation point near the source, then these essentially unbounded. Okay, so we don't want to deal with this unbounded function directly. Okay, and in 2D, even worse, we have this asymptotic property that these asymptotic ansatz even not uniformly accurate close to the source point in even dimension. Okay, so that's the issue. Evelyn Keller realized those issues long time ago, and they able to handle the first case, three-dimensional case, carefully. Then, but the second case, even dimension case, they weren't able to deal with. And Babich used Hadamard methods. Essentially, Hadamard methods was proposed for time-dependent wave equation in time-space domain. Babich used Fourier transform of Hadamard's ansatz, pretend his ansatz that's present here, equation 7. Okay, and okay, so this reference, Bob Birch, he knows that all those different references, and he essentially he dig out that Babich paper, and we use that to handle initialization for solving those corner transport equation. So the issue that, okay, so Babich, the ansatz essentially he proposed a new basis, okay, that's related to from the shallow function. There's a special type basis function, okay, so linked to a Helmholtz function and so on. And once we can insert these ansatz into Helmholtz equation, we will obtain a corner equation again. Okay, that's tau here, a corner equation, omega frequency. Then here Vs, V sub s, the amplitude of not amplitude coefficient, that we call it Babich coefficient or Hadamard coefficient. Okay, because it's different for our understanding of amplitudes. Okay, so we have these. Also, we have a transport equation. Now these ansatz can be initialized easily. Okay, at the source location. Okay, that's there's a actually there's a V sub the coefficient are analytical near the source. We can initialize those things easily. Okay, easily. And so, and next thing is how do we? Okay, now how so? We have developed a systematic way to compute these the quantities. Okay, so essentially we are able to compute the Babich ansatz. Okay, okay, now sorry. Okay, now now we come back to our equation. Okay, now we assume that we have been able to compute the gradient function, Babich ansatz based gradient function, and then we try to use that in our setting. Here we need to make a assumption here. Okay, because the ansatz a corner equation, if we these traditional, if we don't make a careful assumption here, then we will have a caustics happen in our in solving a corner equation and so on. And so we at this stage we assume that the domain V, okay, computed domain V geodesically convex. That means only 2 points in that domain will have a unique geodesic to connect them. And this translates into our computation of the ansatz essentially means that we will have no median into the caustic occurs for this gradient function, okay, at only point source R0 in this domain. So that the ansatz applicable to compute wave fields in this entire domain. Because when we try to use the ansatz, essentially you see that Green function, we each point, okay, we are integrate about source location. Source location are 0 points, point corresponding to one point, a single point source, okay, and then for this point source, we are vary over this domain, and then are also going to be vary this domain V, okay, so we need to make that technical assumption at this stage, but we have already have a way to handle the more complicated case that we are able to deal with caustics induced by media as well, okay. That's some technical assumption we start with, and now okay. So how do we now we just try to discretize this domain, okay, with like some circular cells and by choosing the mesh size, okay. Here mesh size is sort of omega dependent, okay, omega dependent. That's essentially try to give a sample each wave with a fixed number of points. Okay, so that's the omega, it's related to omega. Okay, and so the function right hand side should be also discretized accordingly according to the mesh. Okay, so that's there's some weight function and so on. That's essentially corresponding how do we discretize this source. Okay, and this source discretization here that's very rough as well, just for essentially first order, okay, and we can develop more complicated discretization by using high order discretization that we are not handle here, but that can be done. Okay, so all right, so when the media is homogeneous, then we have exact ansatz, okay, exact these HB integrator will be exact, and then because it is ansatz exact Green function will be okay. And when the media is inhomogeneous and smooth without inducing caustics, then these ansatz accurate in the asymptotic order without truncating these ansatz. Okay, that now our starting assumption that this media is inhomogeneous and smooth without inducing caustics, okay? And then we truncate. And we truncate the ansatz up to the first and second order, first and second terms, okay? Then there's involve the cos square function and V0, V1, okay? And the accuracy will be up to this, okay? Then essentially when D equal to 3, three-dimensional case, if we keep two first two terms, then we will have in three-dimensional case, then we will have 1 over omega square type accuracy. Okay, that's our expectation. Okay, so numerically we will see that it isn't the case. Okay. Okay, so once we discretize and okay, we will have these operator. There's a K volume to volume operator acting on this right hand side I, and that's here because we use V to V, because we in our paper we also deal with the scattering problem. So then these just indicate volume to volume interaction. Okay, so that's then there's the kernel corresponding to Green function. And then some self-term that we need to evaluate the kernel. The kernel self-term corresponding to some technical issue that Bob Burge helped me compute that self-term. Okay, nicely. Okay, it's in our paper, published paper. Okay, and then okay, so then the that's not enough, and then if because we know how to compute this Green function already, so then essentially we can if we can just feed those function, okay, compute the quantity into this the kernel carry out into matrix vector multiplication. Essentially we are done. Okay. okay, the issue that's just like I said, then the computing cost, okay, 3-dimensional computing cost and or large wave number, these computing costs will be very expensive matrix vector product, okay, or in square type of complexity, we don't want to have those kind of high computing cost, okay. So there are two bottlenecks here. We would like to have a fast computation. That if we would like, we need to compute all the green functions, then these are all square type of computing costs. Okay, that's bottleneck one. That's related to computing the Hadamard-Babich ansatz related ingredients. Okay, and then once we handle those first obstacle bottleneck, then we need to assemble those matrix, that matrix kernel, okay? Then carry out the matrix vector product. That again will give us one square type time memory, okay? That we don't have, okay? We are aim at linear complexity algorithm. So these are the two issues. Okay, so first issue, essentially, how do we compute these or compute and store those Hadamard-Babich ingredients? Okay, tau square V0, V1, and those, because those quantity are smooth. Okay, smooth. They are independent of frequency. Okay. Independent of frequency. With that, these are very important. Where our scale separation allows us to separate these guys, the 3D function from these frequency omega. So, and they are smooth, so we can create a low rank representation of this function so that avoid solving corner transport equation for every point source. Okay, so essentially we will carry out some computation, okay, on a very rough mesh, okay, very rough mesh to compute the quantity with high order scheme, and we have then we carry out some kind of interpolation to try to create a low rank representation for those ingredients. Okay, and once we have those ingredients in place, we can repeatedly use them. And second bottleneck that is related to kernel and matrix vector product. Okay, and this again now this guy omega dependent. Okay, omega dependent. Okay, however we then if we directly handle the volume to volume integrate, we will not have a low rank property. It is in fact that kernel has the omega dependent full rank property. Okay, no matter how hard we try, we cannot avoid that full rank property. Okay, so now the trick here, we will use the so-called complementary low rank property of the submatrix of this kernel. Okay, then we will able to compress using the butterfly algorithm to compare the kernel matrix into a product sequence of data sparse matrices. Okay, because we have a matrix vector product. If we have data sparse matrices and we know where those non-zero entries are located, then we can compute those matrix vector product rapidly. Okay, that's the essential idea here. Okay, that's the essential idea. Allows us to speed up the matrix vector product tremendously. Okay, so okay, so here is the first. Okay, the first low rank property of those ingredients. Okay, essentially, like I said, that we will use a very rough mesh to compute those 3 quantity tau square V1. And the idea is that we will lay down triple shift nodes based mesh. Okay, first we choose nodes at the triple shift source location. point source location located at Chebyshev nodes. Then we solve the Econo equation and transport equation to compute the quantity for each individual source location. And then we use Chebyshev interpolation, interpret the computed quantity on the Chebyshev mesh, Chebyshev node mesh. And then repeated the process, eventually we will have Chebyshev low rank representation for these three functions, okay, in this form, equation 11, okay. Essentially, we have in terms of source location, we have Chebyshev extension, and with respect to an observation point, we have a Chebyshev expansion, and in between we have a bridge, okay. That's a bridge kernel F corresponding to computed quantity that we solve the Econo transport equation to obtain the quantity and define these bridge matrix bridge quantity at the Chebyshev nodes location. Then once we have this, then essentially we have a representation on the at each point, each observation point, each source location for these three functions. Okay, that's the low rank representation. Okay, and the others just detail how to do that. Okay. Okay, and then then once we have that, because there's a cardinality of these bridge matrices is very, very small, and then we can sort of use them. Okay, so that's how do okay. So because the Chebyshev interpolation is essentially like has spectral accuracy, then we just need to use not too many points. Okay. Okay. And that's some specific details. Now, once we have those, then we can use blocked version to compute those the quantity ingredients we needed at the mesh locations. Okay, so that's how do we efficiently use that representation. Okay, representation. Essentially, we will use a blockwise structure to use the representation very efficiently. Okay, this give us good speed up in terms of evaluating those ingredients. Okay, but however, that's still not enough for our computation rapidly evaluating that matrix vector product in terms of that kernel matrix. Okay, kernel matrix. Okay, so here still that means we need to do further because that we would have to have O(n) log n argument for that matrix vector product. So this is essential thing based on so-called butterfly algorithm that this algorithm was developed first developed by Michelson. Later on, the Rocklin and others, that's Lachinin and Laurent de Monet, they try to further understand those things, and it happened we use them, had some appreciation of this algorithm, and then that's why I hooked up with Yang Liu, my collaborator at the Berkeley lab, try to use this kind of thing for solving the Helmholtz equation in a general setting. Okay, okay. So this the essence that we need to use so-called complementary low rank property. Okay, so that's the here. Let me see. Okay, so I think that have time to explain this. And okay, so the low rank complementary low rank property, why it is so essential here, let me explain to you. We have kernel matrix here that we just use geometric optical ansatz type kernel to illustrate point, okay? Because away from source, those two answers essentially the same, okay? All right, so okay, so this kernel, when omega fixed, then we can this kernel has a finite epsilon numerical rank, no matter how dense the sample is, okay? So essentially, if we try to approximate the matrix kernel by a finite low rank matrix, as long as we specify that's a very reasonable epsilon, okay, accuracy, then we can have some kind of low rank approximation. However, that low rank structure exists only when the wave fields oversampled per wavelength, okay? That means the intrinsic degree of freedom depends on the omega. And if omega frequency does not change, you oversample, then your matrix becomes larger, kernel becomes larger, but the intrinsic degree of freedom didn't change. Okay, so we can have a low rank structure. But the low rank structure just superficial, because when omega increases, the rank of the kernel will increase. Okay, so then we don't have a obvious low rank structure to explore, to appeal to. Okay, so this is the essential issue here. So what we would have is a uniform fast integration for all omega. Okay, so that's the issue. So this we lead us to consider so-called complementary low rank property. Essentially, we have a source. Okay, source we consider to source location in a domain omega and receiver location in another domain omega r. Okay, so we have a source location and observation location are separated. Okay, so we will consider interaction between them. Okay, between them. Okay, so then okay, so how do we argue that we have a low rank structure? Okay, so assume that the source and receiver domain are well separated, and we consider two small square box in those two domains, BR and BS. Okay, and then we consider the so-called residual phase function. This essentially we have a tau RS. Okay, that's the phase function. S the source and R is the receiver. Okay, then there's a S0 center, R0 center. When these then we have plus minus and so on. Then we have these defined as residual phase function R, capital R. Okay. Okay. Define this. Okay. Then we have we can write the oscillator function kernel oscillator part like this. Okay. Then essentially we have this representation. Okay. And then there's a four term multiplied together. And the first term here that only depends on R, that we have low rank separable representation in term of R. And then second term only depends on varies S. Okay, that we also have then low rank separate representation for the separable representation. And then this third term is constant. Okay, that's good. Then the only thing we need to deal with is that the fourth term. Okay, and essentially whether this factor, okay, fourth factor allows low rank separate representation. Okay, so that's the need some analysis to check this out. Then use the mean value theorem, we can estimate this residual. Now this is the property upper bound. And now if we choose the size of BR and BS, so that their size multiplied together proportional to 1 over omega. Okay, that's essentially allows to control this equation 18. There's two the distant term. Okay, two distant term. Okay, then once we have this, then then uses bounds in our inequality 18, we can see that we essentially can control omega r. That's omega times r is bounded, okay, bounded. And basically for this quantity bounded, then this guy as a non-oscillatory, then we have a low rank separable representation. Okay, so that's allows to have now this guy have low rank separable representation, then we have this thing. Okay, and then this issue that how do we enforce the kind of assumption? Okay, enforce such kind of structure. This butterfly algorithm try to do. Okay, that's lead us to very complicated algorithms. Okay, that I don't want to go to all the details here. This slide just show you that we indeed we have this algorithm. Okay, okay. So I'm not going to too much detail here. Essentially, how do we try to exploit these try to enforce these complementary low rank property in this form. Okay, that's essentially related to how do we partition that matrix into various subblocks and enforce those, all those structure so that we can have the rank information comes out. Okay, so there's okay, so that essentially eventually we have a bunch of these sparse matrix multiplied together. We know what those where those non-zero entries are located. Then we can multiply them accordingly. Okay, so that's an issue. That's an argument essential point. Okay, so all those detailed rank estimate and in our published work. Okay, so if you are interested, you can go to my website. Also, is published in multi-scale scaling, multi-scale simulation modeling. Okay, modeling and simulation. Okay, okay. So so that's some other technical detail. Let me just show you examples. Some examples to try to say that our algorithm give us the right thing. Okay, so here's a inhomogeneous media, some pseudo media. We have example omega equal to 80 pi. That's they essentially give us 50 wavelengths per each direction. Okay, and there's right, left. That's corresponding points. I think the point source. There's the wave field. Then in the middle we have a difference between our solution and the fine difference solution. Fine difference solution we have to use a very oversampling. Okay, very more than 50 points per wavelength to get a reasonable solution, so that we can compare. Okay, that's neat. Then in the logarithmic scale, that's the difference very small. If we plot on slides some lines, that's the same. Okay, here essentially here we are plotting the magnitude rather than the waveform directly. If waveform directly, then we cannot see lots of change. Here that you see, still you can see lots of small difference between our solution and the fine difference solution. Okay. Okay, so here they're not just the same thing with different right-hand side. Now it's a Gaussian wave packets. Okay, Gaussian wave packet. Okay, that's the propagated along one direction power. There's a difference, and then there's a in terms of comparison. Okay, comparison along one line. Okay, here we just use 10 points per wavelength, and but to find a different match, we need 50 points per wavelength. Otherwise, we cannot compare those two solutions. Okay. So this is the scattering problem that we have some hard obstacle in the domain. Okay, so that's some here we have some caustic here effect here. There's a comparison. Okay. Okay, so now we also can handle caustic induced by right hand side. Now here, if we have a concave kite-shaped source, okay, then we have the concave region that at this location there's rays hit the concave part, then we will have the refractor ray somehow will intersect with each other, then we will have caustic in the region. Okay, so that's we can handle. That means we can handle caustic induced by right hand side. Okay, and the difference, and you see that again we just use a free 10-point per wavelength. Okay, and this 3D now 3D-dimensional case. In the case we have an exact solution. You see that exact solution in inhomogeneous media, constant gradient. And you see that our methods just use a 4.5 point per wavelength. We are able to get a reasonable solution. Now direct methods use the same number of points per wavelength, then we it gets a solution like this. Okay, that's the pollution error. Okay, pollution error. And there's moreover, there's found different. Okay, that's the found different methods developed by my collaborator Liu Yang. That's the state-of-art solver. Okay, that's the here is only at that scale that we have like 20 million unknowns for direct methods. Okay. And more than that, so there is no sparse direct solver can handle more than that. Okay, so our method just need to, we can go only need like 70 million, and we can even go to higher frequency. That's no problem. Okay, that's some kind of convergence. Okay, so for computer ingredients, we have we have desired accuracy, so that's no problem. And then wave fields. Okay, we have a first order convergence, the second order convergence. Here, that's on the top right figure. For that's the first line corresponding to first order convergence. First order convergence. That's essentially that's expected. Then from the second line corresponding to second order convergence, because you see that because second order convergence, that means these term will be competing with each other. When these one first term, for example, dominates, then other terms are small, then we can preserve first order convergence. And then in the second order case, because the first term will be dominant for a short, will be become very small quickly, that we preserve this kind of funny convergence behavior. But it's just said that when these first when these other term are not dominant, then we will have preserve first order convergence, second order convergence. Now this term essentially related to computing this accuracy in the computed ingredients. Okay, that's this kind of ingredient accuracy we can control. We can use always computed ingredients with a more accurate scheme, or find a mesh that is other term less dominant, less influential, so that the essentially first term will be dominant. Then we will have second order convergence. Okay. All right. So the complexity essentially says that we have a O(n) log n type of complexity in our algorithm. Okay, for our algorithm. Okay. Again, this is for 2D or 3D. Okay. So let me also show you a few figures related to the imaging. Okay. That's imaging. We have a sinusoidal model. Now, this case, essentially because image problem, we have to deal with some kind of caustics, and so here we use Huygens principle and plus these our Hadamard-Babich ansatz computed quantities and to carry out the image. Okay, this is caustics. We have caustic here, that's by retracing. And then this we compare with okay, there's a last one here that's corresponding to our Huygens principle based downwards wave extrapolation. Okay, and the other methods, E corresponding to reverse time migration. So those two methods can compare with each other. Other standard migration methods cannot handle the caustics easily. Okay, we can see all different artifacts here. There's a comparison just we carry out the comparison in a very rough manner. If we think that if we take care of those things carefully, probably we can achieve better results. In the point that I would say that our methods can handle the caustics easily. Okay, and we would like image this horizontal layer by using, if we take care of caustics, and then we are able to image this fat layer clearly. If we don't take care of caustic, then we will have the kind of strange smiling issue, so related to downward wave propagation. Okay, so let me conclude. Okay, so we have developed a fast butterfly comparison integrator for Helmholtz equation. Enjoy some unique features, and we can use these equations to solve a wave Helmholtz equation for multiple frequency, multiple right-hand side. Can be used for imaging problem. There's ongoing work. Also, Babich answers only he only able to propose answers for Helmholtz equation. For Maxwell equation, elastic wave equation, it was sort of developed by us. Okay, and that's my postdoc and the postdoc, and also with Babich, we did that for Maxwell and for elastic wave equation. And because we need those things for our solver, so we come up happen to realize that those issues not solved yet. So we sort of able to deal with those issues. Okay, so we also certainly then once we have those things, we can develop a butterfly algorithm for those equations as well. Okay. All right, so I will thank NSF for the support over the years. Otherwise, I cannot have those results to show you here today. I would thank NSF, and thanks everybody. I'll stop here.
Thank you so much, Jianliang. Very nice combination of tools. Very nice talk. So if anyone have questions, please unmute yourself and you can ask questions.
Yeah, feel free, because okay. So I know there's a lot of argument aspect. Also, the tools are not so familiar with many of you. Okay, so just feel free. Okay, yeah.
So I was wondering, so in some sense, main assumptions is sort of you have a scale separation, right? And
yes.
Smoothness of the medium. So what is your experience? Are you robust with respect to these assumptions, or geometric optics may work even though you push these assumptions a bit? What is your experience with this formulation?
Okay, so I think that we assume that media is smooth. But this kind of smoothness essentially relative to wavelengths. I think that okay, so if the medium sort of a little bit rough relatively, then if we use even shorter wavelengths then to handle this rough medium, then it's still okay. I think that's my understanding. Okay, so essentially there's a kind of scale separation is relative. We should understand those in a relative sense rather than absolute sense. Okay, so that's my understanding. It's a very useful tools. Okay, so even if you have rough media, but then then we should in those settings we should go into even smaller wavelengths. Okay, that's to use the tools, because these your media variation has a certain scale, and then we use geometric optics. Then we just use to sort of use geometric optics as a tool to measure those kind of variation. That means we should use a very small unit in terms of wavelengths. And then that means we still we should be able to use that. And then in that setting, the cost probably depends on the situation. Cost are really high. You need to use go to a very extremely high frequency. Yeah, that's my understanding. Yeah.
Thanks.
Yeah. So
any other questions, Jianliang?
Mm-hmm. Thanks, Michael.
So just one final question. One more question. Yeah. So also, before you worked also on the parallax regime. Let's say that you have a very narrow beam.
Yes.
Would it be well adapted to this framework? Could adapt it to such configuration?
Yes. So if you have a very narrow beam, so certainly that okay. So sorry. Yeah. So if you have right hand side, if you have a Gaussian wave packet, then we can also have a right hand side. We have a like a narrow beam. So that's no problem. Okay. Then if you have a nowadays you have a narrow beams as a source, then there's essentially we just replace this right hand side with a narrow beam. That's okay. Okay, so that's or we can even try to develop these the starting on the beam, your beam develop the ansatz. Okay, so that's should be doable. Yeah.
Well, if there are no more questions, we are at the hour. So thanks again, Jianliang, for a very, very nice talk, interesting techniques. Thanks also to everyone for coming to our seminar today.